Valence bond theory could not explain clearly the bond strength, bond order, and magnetic behavior of molecules. Thus, a new theory called the molecular orbital theory was introduced by Frederick Hund and Robert S. Mulliken in 1932. Now, before going into all this, I would like to recall the fact that the atomic orbitals are nothing but are solutions of Schrödinger wave equation called wave function denoted by psi, and represent the space where there is maximum probability of finding an electron. Now, a molecular orbital is formed by linear combination of two atomic orbitals of comparable energies and of proper symmetry. We know from the wave theory that in a wave there is a positive phase as well as a negative phase. When one wave interferes with another wave, then there are two ways of doing so. If the two waves are in the same phase, then the interference is called constructive interference. And the individual waves add up to give a wave like this. When the two waves are out of phase, then the interference is called destructive interference, and the individual waves cancel out each other, and there is no resultant wave at all. The first five solutions of the Schrödinger wave equation gives rise to five wave functions represented by five atomic orbitals. The blue portion stands for negative phase and the red portion stands for positive phase. Note that the blue portion cannot be viewed in the s orbital because they lie inside the red sphere. As I have already mentioned, that combination of atomic orbitals, say psi A and psi B, can happen in two ways. They may be added up, that is constructive interference, or they may cancel out each other, as in destructive interference. For constructive interference, say for hydrogen molecule where two 1s orbitals are involved, the position of the nucleus is here. The orbitals are in the same phase, so when they combine, this portion gets added up and the molecular orbital forms like this and is known as sigma 1s. Notice that the molecular orbital is delocalized over the entire molecule. The molecular orbital has two hydrogen nuclei at its center, just like an ellipse has two foci. Therefore, molecular orbital is polycentric, unlike atomic orbital, which is monocentric. The two nuclei are bonded together by this space over here, which has dense negative charge. So this molecular orbital helps in bond formation and is therefore called bonding molecular orbital. The energy of the bonding molecular orbital is less than combining atomic orbitals because the negative charge is more delocalized and is therefore more stable. When the two atomic orbitals are out of phase, say one is red, that is positive phase, and one is blue, that is negative phase, when they combine, this portion vanishes. The molecular orbital formed is like this and is known as sigma asterisk 1s, where asterisk means anti-bonding. This molecular orbital has a blank space in between the nuclei, where there is no probability of finding an electron and is called nodal surface. The two nuclei are therefore exposed to each other and there exists a strong repelling force. Thus, this molecular orbital tries to break the bond formation and is therefore called the anti-bonding molecular orbital. This molecular orbital is of higher energy than the combining atomic orbitals, this high energy being required to keep the nuclei in their unfavorable positions. Remember that SS overlap is always sigma overlap. Now if we arbitrarily choose z-axis as the axis of bond formation, then 2pz undergo sigma or end-on overlap and the 2px and 2py orbital undergo pi or side-on overlap. In the following animation, we will see the formation of pp sigma overlap and pp pi overlap. A chemical bond is possible only if the number of bonding orbital electrons exceed the number of anti-bonding orbital electrons. Now we will restrict our discussion to homonuclear diatomic molecules of the first and second period elements only. The energy orbital diagram of the first period elements is like this. It has only hydrogen and helium having only one s atomic orbital. For hydrogen molecule, the two electrons are here before bond formation. The filling up of molecular orbitals follow the same rules as the filling up of atomic orbitals, like above principle, where the lowest energy orbitals are filled up first. The Hund's rule, where degenerate orbitals having the same energy pair up only after each one of them is filled up by a single electron. The Pauli's exclusion principle, which states that the two electrons in an orbital should be of opposite spin. So the electrons in hydrogen molecule fill up like this. Now there is a formula for finding the bond order, which is bond order equals number of bonding molecular orbital electrons minus number of anti-bonding molecular orbital electrons divided by 2. For hydrogen, it is 2 minus 0 divided by 2, which is equal to 1. The value matches with our concept. There are no unpaired electrons in the molecular orbital, therefore it is diamagnetic and is repelled in a magnetic field. For helium, which has two electrons in the 1s orbital, the hypothetical helium molecule has molecular orbitals which are filled up like this. The bond order is 2 minus 2 divided by 2, that is 0. Thus, helium molecule does not exist. Let us go to the second period. The energy orbital diagram is like this. Note that the pi 2px and pi 2py orbital energy is less than the sigma 2pz orbital for elements having atomic number less than 8. This is because of the small size of the nuclei, which is responsible for strong pi overlap. For boron, which has atomic number 5, the filling up of molecular orbitals are like this. The bond order is 1. Due to the presence of unpaired electrons, it is paramagnetic and is attracted by a magnetic field. For carbon, which has atomic number 6, and the filling up of molecular orbitals are like this. The bond order is 2 and it is diamagnetic. The double bond of C2 molecule, which exists in vapor phase, seem to be of two pi bonds with same bond dissociation energy. This is supported by the molecular orbital theory. For oxygen, which has atomic number 8, the energy orbital diagram is a bit different from the previous one. Here the sigma 2pz orbital is of lower energy because pi 2px and pi 2py orbitals are not so strong. Note that the extent of pi overlap reduces with the increasing size of nucleus. The filling up of molecular orbitals are like this. The bond order is 2 and it is paramagnetic.